Ladies and gentlemen, in a brief moment, our lecture is about to continue. Before we start, we would kindly ask your cooperation to turn off your audio. Thank you. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon for all of us here. I hope that all of us present in this lovely afternoon have all enjoyed our short break and are ready to indulge on another resourceful and knowledgeable lecture. So before we start, first please let me introduce myself. My name is Fanny, and I'm the graduate student of Faculty of Pharmacy, University of Indonesia, and I will be your Master of Ceremony for this virtual summer course session. Ladies and gentlemen, thank you very much for joining us on this afternoon for another session of the Faculty of Pharmacy Universitas Indonesia Virtual Summer Course 2022 Advanced in Pharmaceutical Science. Welcome everyone to this virtual summer course held by the Faculty of Pharmacy Universitas Indonesia. First, I would like to greet our honorable guests for this afternoon. First, the honorable speaker for today's lecture, Associated Professor Dr. Nguyen Tu Ha from the School of Chemical Engineering, Hanoi University of Science and Technology of Vietnam. Second, the honorable moderator, Dr. Apotheker Febrina Amelia Putri, Magister Pharmacy from the Faculty of Pharmacy Universitas Indonesia. The honorable professors, lecturers, and all faculty members who are present in today's lecture. And last but not least, I would also like to greet all audience and participants. This summer course is aimed for students and fresh graduates who are interested in increasing their knowledge of pharmaceutical science with a broader perspective because we have invited professors and lecturers from the University of Indonesia itself and also a lot other well-known universities abroad. And on this afternoon, we will have our fourth lecture from Associated Professor Dr. Nguyen Tu Ha with the title of Hydrogel based on cellulose, preparation and application. This lecture will be presented by Professor Nguyen and moderated by Dr. Apotheker Febrina Amelia Saputri, Magister Pharmacy. But before we begin the lecture, please let me read a brief introduction of this session moderator, Mrs. Dr. Apotheker Febrina Amelia Saputri, Magister Pharmacy. Mrs. Febrina Amelia Saputri is a lecturer in the Faculty of Pharmacy Universitas Indonesia, and in 2019, she finishes her doctoral degree from the Department of Pharmaceutical Science and Medicinal Chemistry, Faculty of Pharmacy, Pajajaran University. She is one of the members of the Laboratory of Pharmaceutical Medicinal Chemistry and Bioanalysis, Faculty of Pharmacy, University of Indonesia. Her research interest area is pharmaceutical chemistry analysis, and her recent publication is a sensitive bioanalytical method for the simultaneous determination of amlodipine and glibenclamide. All right, without further ado, please give a warm welcome to our honorable moderator, Dr. Apotheker Febrina Amelia Saputri, Magister Pharmacy.
Okay, thank you, MC, for the introduction. Good afternoon, everyone. My name is Febrina Amelia Saputri, and today I will be your moderator. As mentioned by the MC, today's lecture topic is Polymer, Advanced Technology in Pharmaceutical Application. And before we begin the webinar, please allow me to read the speaker's curriculum vitae. Associate Professor Nguyen Tu Ha is a lecturer and researcher at the School of Chemical Engineering, Hanoi University of Science and Technology, Hanoi, Vietnam. She obtained her Bachelor of Chemistry from Hanoi National University of Education, Vietnam in 2007. Then she continued her studies into master's course and got her Master of Physical Chemistry at Hanoi National University of Education, Vietnam in 2009. In 2012 until 2015, she pursued her doctoral studies and got her Doctor of Engineering degree from the Material Science program at Nagaoka University of Technology, Japan. Before coming back to Vietnam, she was working as a postdoctoral researcher at the Department of Material Science and Engineering, Tokyo Institute of Technology, Japan, investigating the morphology of soft materials through SEM and TEM. Her recent publication, entitled Cellulose Grafted with Polyaniline for Simultaneous Absorption of Cationic and Anionic Dyes in Water Effluents. Okay, without further ado, please welcome our Honorable Lecturer, Associate Professor Nguyen Tuha. Associate Professor Nguyen Tuha, the time and screen are yours. Yes, the time and screen is yours.
Okay. Okay. Thank you, Fabrina Amelia, for the nice introduction. Can you hear me?
Yes.
Okay. Okay. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, am I right so far? Okay, today I would like to present about the research work about the hydrogel based on cellulose, the preparation and application. This work is done in my university and also with the collaboration with NICE, the Nara Institute of Science and Technology, Japan. This is a collaboration work. Okay.
Okay, sorry, doctor, can you make it full screen? Yeah.
Okay.
Great.
Okay, so now I would like to start. This is in my presentation. There is four parts. The first part is introduction. The second is preparation and characterization. The third part is application, and finally is conclusion. So here is the first part. I would like to make a short introduction about first the polysaccharides. As you may know, polysaccharide is very popular in the earth. It may be one of the most abundant resource in our planet. It comes from many biomass plants. For example, here is some kinds of polysaccharides. For example, cellulose. Cellulose we can take from sugarcane baggies or rice husk or the coconut husk. Some kinds of polysaccharides such as galactan. Maybe you are also very popular with galactan. Galactan is extract from the seaweed. Maybe Vietnam or Indonesia have very long coastal. That's why I think that seaweed is very popular in both our country and also your country. So galactan is a kind of polysaccharide. One more thing is chitin and chitosan. You see, chitin and chitosan, actually chitin is a natural polysaccharide is taken from the cell of some animals such as shrimp or crab. It's also very popular, especially in the ocean. And that's why we want to concentrate on polysaccharide. But in fact, cellulose, here we would like to focus on cellulose. Cellulose is very popular and very famous. There is a lot of research works focused on cellulose. From cellulose, we can make many kinds of materials. We can either modify cellulose or cellulose itself can be used as a raw material for some research form to prepare many novel materials. Because of the exhaustion of petroleum and the pollutant issues regarding petroleum derived polymers, so that's why polysaccharides is renewable materials. It is have potential to replace petroleum-derived polymers. And that's why in this research work, we want to concentrate on cellulose. So now I want to make some introductions for you to understand more about the cellulose. I know that, of course, cellulose is very popular for us, but still want to introduce something. Cellulose is a naturally occurring polysaccharide. Here, it takes from the biomass and plant. The composition, this is the compositions of the in biomass. Inside the biomass, there are plant fiber, and this is the composition of plant fiber. You can see here, in plant fiber, it have first cellulose. Usually, for the most tree in the tropical country, the cellulose takes around from 30 to 40% in plant fiber. The other ingredient is hemicellulose and lignin. Here, I would like to show you the structure of cellulose, hemicellulose, and lignin. Okay, you see here. Please wait for a while. Because cellulose is only around 30 to 40%. The hemicellulose is about 20%, and the remain is lignin. But the problem is hemicellulose and lignin is quite weak. That's why it can affect to the properties of cellulose. Before using the cellulose, we should remove hemicellulose and lignin from the plant fiber. So in order to get the cellulose. So that's why you see here, I want to show observe how you can see how a plant fiber in detail. Here is here I want to show you in detail. This is biomass plant when you cut the fiber. This is a biomass plant, and then you see in the cells of biomass plants there is a fiber. This fiber is content of lignin, hemicellulose, and cellulose. So these three ingredients inside a fiber. Actually, besides lignin, hemicellulose, or cellulose, there are also the other ingredients, but it's the minor ingredient. That's why we can easily to remove. But you see here, lignin and hemicellulose is quite stuck. It can make a strong connection with cellulose. That's why it's quite easy. It's quite difficult to remove lignin and hemicellulose completely from the fiber to get cellulose. But we have to remove lignin and hemicellulose because as you mentioned, as I just mentioned now, lignin and hemicellulose can make the weaken in cellulose. So in the fiber, here, this is nanocellulose. Nanocellulose, you can see here. Inside the fiber, this is nanocellulose. Okay, I will tell you about the nanocellulose later. But here, just keep in mind that nanocellulose is inside the fiber. So we have to remove lignin and hemicellulose, then we can take nanocellulose. Why we call it nanocellulose? Because there is a diameter, there is a dimension in nanoscale. This is the width of nanocellulose in nanoscale. But the length of nanocellulose is quite long. It depends on the resource. For example, from the sugarcane baggies, or from the wood, or from the rice wood, the size of nanocellulose is different. I mean, the length of nanocellulose is quite long. Okay. And when we cut the fiber, we can see this. Okay, maybe it's more clearly for you to see this. Here is, you can see lignin is surround, and then after lignin is hemicellulose, and then inside a fiber is the nanocellulose. So if we want to take nanocellulose, so we have to remove first lignin and then hemicellulose. And then when you also cut the fiber, but in as a surface, you can easily see this. In nanocellulose, there is two reasons. The first one we call crystalline reasons, and the second one is amorphous reasons. Actually, also it depends on the resource of the biomass plants. The ratio between crystal and amorphous reasons may be different. If the resource is quite hard, I mean, when the biomass plants is hard, for example, it's wood or bamboo tree, so the crystalline resin is the amount of crystalline resin is much higher than amorphous resins. But for the other biomass plants, which is short, so the amorphous resins usually is the ratio, the amount of amorphous resin is higher than crystalline resin. We have to keep in mind this because we've been concerned about the aim, what we want to use for nanocellulose. So we want to take either crystalline resin or amorphous resins. So usually we will select the resource of biomass plant. Okay. So now we can observe the structure of nanocellulose. We will focus on nanocellulose. This is nanocellulose, the crystalline resin and amorphous resin. Actually, in cellulose, there is a polymer chains. Okay, I will mention about the chains of cellulose later. But here you see between the molecule, the polymer molecule, there is a strong connection that is usually hydrogen bonding. So they can stack together to make the crystalline resin. But when the connection between when the interaction between the chains is not strong, so we will have amorphous resins. Usually, if we want to break cellulose, we have to attack on amorphous resin first, and then from amorphous resins, so we can after it is broken, then we can attack to crystalline resins. But for some kinds of application, we also need crystalline. In such a case, we also attack on amorphous resins. And then we take the nanocrystal. Okay, this nanocrystal is very strong. It's very difficult to break the chains in nanocrystal. So also it can find their own application. So how can we get this nanocrystal? Of course, usually we use some acid hydrolysis. For acid hydrolysis, we can step by step remove lignin and then remove hemicellulose. Finally, we will get the amorphous resins. Actually, I'm sorry, we will get the nanocrystal with amorphous resin and crystalline resin. Actually, the nanocrystal is very difficult to be broken. That's why after acid hydrolysis, so we can easily to get the nanocrystals. Okay, and now this is the way to just now I mentioned about the resource of materials we use, that is cellulose. So usually in our research work, we take cellulose from the biomass plant in Vietnam, sugarcane baggies or coconut husk or rice husk is very common. So we can easily take this. And after we gather this resource, we have to make some steps to remove hemicellulose and lignin. So, but not only cellulose from biomass, we also concerns on the paper. Yes, you can, of course, you may know that the paper is made from cellulose. So after we use the paper, someone just throw away, but we can gather the waste paper and make it as our starting materials for our research work. So this is another candidate for cellulose resource is paper. Here is the process of paper production. Of course, maybe some here, maybe many people knows how can we make a paper, but I just want to mention again, from wood we will cut into very small chips, and then we cook the chips with the high temperature, high pressure, and high pH. We will put the sodium hydroxide and sodium sulfide to mix with the wood chips, and then under high temperature and high pressure, we will get something like a paste. We can call it like a colloid. And then in this step, when we use high pH, it means we already remove lignin. So when we remove lignin, the hard work is the back liquor is contain lignin. We can use lignin for another purpose. The thing we get is hardwood. This one is washing with water. For this, in this step, when washing with water, also hemicellulose is removed. And then we bleaching. In this step, when we bleaching, so the other ingredients like ash or dash was also removed. And then we get the bleach pump. It is quite wide, and sharp. Finally, this bleach pump is ready for making sheet paper. Okay, this is the way how a paper is produced. But then with the paper, it's already cellulose. But usually not many people is interested in paper, because the purpose of paper, the aims for paper, the application for paper, just for use for writing. But now we are so concerned after writing, after we use paper. So what we do is also a very good resource of cellulose. That's why in our research work, we use two kinds of cellulose. That is, the first one is from biomass plant, and the second one is from waste paper, the waste paper. I mean, the paper after using. In the other research work, usually they focus on pure cellulose. It is cellulose is commercialized and available commercialized, and they use it and make the very good materials. But in our case, we want to utilize, we want to use the cellulose from natural resource and the resource from the daily life. Okay, so now, so this is the two kinds of cellulose we use in our research work. Sometimes we also do, and we also compare between the results between two materials. So now, okay, I would like to show you about the structure of cellulose molecule. Now, this is the structure of cellulose molecule. It is a non-branch chain. The unit in cellulose is beta-D-glucose. Usually, we just know the unit is C6, S10, and O5. But this unit will make a very long chain, and the molecular weight of a chain is around 5,000 to 40,000 Dalton. And here you can see in this, okay, I will show you. Okay, you can see in the figure here, this is the first, for example, this is the first chain cellulose, and this is the second chain of cellulose. Of course, there are many chains in cellulose crystal, and between the chains there is a connection. You see here with this blue. Okay, the bond here I write as the blue. The blue one is actually hydrogen bonding. So between the cellulose chains, there are very strong bonding between O and S. That's why, as I mentioned before, the nanocrystal is very hard and very difficult to be broken. That's why you see in cellulose, there are many OH groups, but it's quite difficult to dissolve in water. Yes, very difficult to dissolve cellulose in water. If we want to dissolve cellulose in water, we have to break the hydrogen bond. Yes, once we can break the hydrogen bond, so the chains will be separated. The cellulose chains will be separated. With one chain, it's easier to be dissolved in water. That's why if in the crystalline region, the hydrogen bonding is very strong. But in amorphous region, the space between cellular chains is quite far. That's why we are easily to break the chains in amorphous region. Here we also in our work we focus on amorphous regions because we want to take exchange of polymers to make a hydrogel. That's why we try to break the hydrogen bond during our research work. Only when we can break the hydrogen bond, then we can rearrange the cellulose to make the materials as we want. Okay, and because for this we okay now we sorry for wait for a moment. Okay, so with cellulose, because it's a green materials, renewable materials, so we want to prepare many materials based on cellulose. But how can we do with this cellulose? Here, in this work, we use cellulose as a starting materials for prepare hydrogel. Because you see here in cellulose chains, there are a lot of OH group. With this OH group, it's easy to make a hydrogel as long as we can separate chains of cellulose. So that's why we think that we use only cellulose chains to make a hydrogel. So what is hydrogel? Maybe you also know about the hydrogel, but here I want to show you something about the hydrogel. Hydrogel is a hydrophilic polymer with 3D network structure. Yes, because in cellulose, there is a lot of OH group. That's why it can easily to make a hydrophilic polymer. Then with its chains of cellulose, we can make 3D network structure. Hydrogel can absorb a large amount of water. Sometimes a hydrogel can absorb the amount with around 4 times or 5 times work. 4 times or 5 times weight of a hydrogel. So it's a very, very, very unique properties of this such materials. One more thing is the special of the structure of hydrogel. It can keep small molecules or ion in 3D network because it makes a network. So small molecule, for example, for example, water, of course, or some gas molecule can be trapped inside the 3D network. And some kinds of ion also can be trapped in this network. For example, lithium, sodium, or silver ion can be trapped in the 3D network. That's why from hydrogel, we can prepare many kinds of materials with the new properties, as long as we can insert the small molecule or ion in the network of hydrophilic. One more thing, with this kind of structure is there are a lot of voids inside the structure. So hydrogel can be the medium for the transportation of ions. For example, if we want some kinds of ion, for example, potassium or sodium transport through this hydrogel. So it can, because the structure, the 3D network is the constant, but the ion can be transported through this network. From hydrogel, see, this is the defined structure of hydrogel. But from cellulose, we can prepare a hydrogel. This is the hydrogen film based on cellulose we prepare in our laboratory. This based on cellulose. Hydrogel based on cellulose, of course, is a green materials. Because it's made from cellulose, so it can be easily to be biodegraded. And because it's made from cellulose, so it's also biocompatible materials. It has some novel properties like self-healed materials. Or because it's a hydrogel, so it is a flexible membrane. From this film, we can prepare, we can add some small molecule or add some ion to make a new materials based on this hydrogel film. Okay, now I will mention more about the hydrogel cellulose. Actually, the hydrogel based on cellulose is not so strange at all. It's available in our daily life. Here, you can see it's very popular in our daily life. It is, someone may know that it used in agriculture because it can keep water inside. So it can, if the sun is dried, we can use hydrogel to make the humidity for the soil. And sometimes if in a flat, a lot of rain, a lot of water in the oil, in the sun. So we can use hydrogel to absorb water. So hydrogel is widely used in agriculture. It's also widely used in tissue engineering. Yes, I think you know, all of you know about this application. Or hydrogel is used in disposal diapers. It can use as drug delivery because as I mentioned, it's made from the hydrogel, made from cellulose. That's why it's very biocompatible. So we can use as a drug delivery, or we use as a contact lens, or use for wound dressing. Yes, it's very common. It's very popular application of hydrogel based on cellulose. However, because please look at this again. Due to the different links between different linkages in 3D network, the properties of hydrogel is very different. I mean, here you see this we call this network. In this network, you can see these different linkages in the 3D network. So the properties of hydrogel is very different. Just now, I mentioned about some application of hydrogel based on cellulose, but it's just common application. When we can change the linkage in the 3D network, we can prepare, we can synthesize very new materials with very new properties. Either it depends on the properties of the linkages in hydrogel. So the hydrogel can be very strong or very weak. It's very easy to absorb water, but it can absorb water very little. So it depends on the chemical, the linkages in 3D network. So now I want to tell something about the linkages in 3D network. The linkages in 3D network may be physical linkages. Here, I want to show you some method to prepare physical linkages in the hydrogel based on cellulose. The physical linkages may be hydrogen bonding. Here, for example, we have, this is an example. From sodium salt of carboxymethyl cellulose, we can use chlorhydric acid. So to make the hydrogen bonding between the chains of the cellulose. And then because of hydrogen bonds, so hydrogel is formed. Of course, hydrogen bonding is quite weak. That's why if the hydrogel contain hydrogen bonding is quite soft and easy to be broken. The second another kind of physical linkages is the physical cross-link formed through the cold heat process. This is one example. For example, here is not cellulose. Here is galactan. Is a galactan. From kappa carrageenan in solution. First, we can cool and then heat, and finally, after the process of cold and heat process, the shape of the chain of the carrageenan is changed. After it changes, it can stack together and to make a physical cross-link. Also, the physical cross-link is also soft. So that's why we can easily to break this kind of hydrogel. And that's why for this process, we can prepare the hydrogel just for some application in, for example, in medicine or in food. That's all. But when we want to make some high performance materials, we cannot use this process. One more thing is coagulate. Coagulate to make the physical linkages. This is one example. When we have anionic polymers, for example, is some kinds of galactan, for example, agar-agar, and then we mix with a cationic polymer. Then we obtain the complex co-activated polyion complex hydrogel. It means the ionic and the cationic can interact together to make a hydrogel. In this case, the hydrogel is quite hard, and the tensile is quite strong. We can use this method to prepare the hydrogel, but actually also quite difficult to find the suitable anionic polymer and cationic polymer. That's why this method only can apply for several cellulose, not for all. One thing is now is very common now, very popular now, that one is chemical linkages. In this method, we use the cross-linking agent to make the chemical cross-linking. Here is some example. For example, we have two stacks of cellulose nanocrystals, and then we can use some cross-linking agent to make the, you can imagine, we can make the connection between the nanocrystal, and then we have the hydrogel based on cellulose. This is very, with this method, we can easily to prepare the hydrogel, the hydrogels, as long as we find the suitable cross-linking agent. And one more thing, hydrogel prepared, synthesized from this method is very hard and it's very strong. That's why we can use for many purposes. So in our research work, usually our research is find the suitable cross-linking agent to make the hydrogel bonding. To make the hydrogel, and with this hydrogel, we can prepare for many purposes of application. So now I want to now I want to introduce to the second part of my presentation, is preparation and characterization of the hydrogel and the materials we prepare. Okay. Okay. First, as I mentioned before, we want to take the cellulose from biomass plant. So the first step in our laboratory, either we can take cellulose from biomass or take from the waste paper. Here is the purification of cellulose from biomass. From biomass, first we shock. Okay, let me show you. First, we shock in chlorhydric acid for around 4 hours at 50 to 60 degrees C, and then wash in distilled water until pH equal 7. It means we will remove all acids in this step. For this first step is for remove the hemicellulose and lignin completely, to remove the both lignin and hemicellulose, hemicellulose, and we get the powder one. In the second step, we shock in sodium hydroxide, also for 4 hours, 50 to 60 degrees C, and then we wash in distilled water until neutral media. After this step, both lignin is removed completely from our materials, and we get the powder 2. With this powder 2, we also shock in sodium chloride, hypochlorite, and wash in distilled water. This step also for bleaching. And then we filter and dry, we get cellulose. With this, actually, this procedure is not from our laboratory. It's well established, and we can find in many references, in many research work is published. But here, the only thing is we applied with the biomass we get in Vietnam. For example, coconut husk, sugarcane berries, or rice husk. something we also use, we apply this procedure to prepare cellulose from bamboo, the bamboo fiber, or some kinds of biomass in our country. So from the biomass, for example, this is sugarcane berries. Yes, very popular in my country. And then finally, we get this one is cellulose. Cellulose is cut in very small size, and this is ready to prepare hydrogel. And we have to find the way to prepare such a material to become a hydrogel. Okay, and this is the preparation of hydrogel, of cellulose hydrogel. Okay, this is our procedure. This procedure is established in our laboratory. From cellulose, we get, just now I mentioned how to we collect the cellulose from biomass plant. We also can use cellulose from paper. First, we have to soak. We have to soak the cellulose, immerse cellulose in sodium hydroxide solution. When we soak in hydroxide solution, so okay, in this step, so we can get a very viscous solution. Of course, this is the colloid solution. We have to soak in the concentration of hydroxide, of sodium hydroxide is about 40% weight by weight, and in 60 degrees C for 30 minutes. Then we get a very viscous solution. After that, we also drop the chlorhydroxide acid solution inside the viscous solution in order to get the neutral medium. It means pH equals 7. Then we get the cellulose colloids. It's also very viscous. And then after that, we add acrylic acid. This one is a cross-linking junction. So this is a cross-linking. Okay, I want to explain more. After the first step in cellulose colloid, so we can separate the nanocrystal of cellulose. And then in this step, in the third, we add acrylic acid. This one is cross-linking agent. And then we add ammonium sulfate. This is initiator. This initiator will make the chemical reaction between acrylic acid and the cellulose. So it makes a junction between cellulose. And finally, this one is NN methylene bisacrylamide. This one is for the firm, to make the firm connection between cellulose crystalline. So after this step, we get cellulose hydrogel. From cellulose is very hard. Cellulose is not, of course, is transparent. Is not transparent. Cellulose cannot dissolve in water, and then finally we get cellulose hydrogel. This cellulose hydrogel is very easy to absorb water, and sometimes when we change the amount of acrylic acid, so we can get very transparent the cellulose hydrogel. Okay, so this in our laboratory now, we can prepare the cellulose hydrogel with many properties we want. And here is some characteristic of the hydrogel we already prepared. Here, I want to show FTIR spectrum for cellulose hydrogels. This is the FTIR spectrum for cellulose. Of course, we can see many characteristic signals of cellulose hydrogel. After makes the hydrogels, it means when we add the acrylic acid, ammonium persulfate, and something for cross-linking agent. Here we get the hydrogel. This is FTIR spectrum for hydrogel, for cellulose hydrogel. This is the cellulose as the hydrogel with different amount of cross-linking agent. Okay, I'm sorry. Just for a while. I'm sorry, wait for a while. Okay. Oh, you can see here and compare. After we make hydrogels, the spectrum is quite similar. The only thing is we see that here the amount of water inside hydrogel is much more than in cellulose. Of course, when you see the peak at about 3,200, more than 3,100 is quite big. It means water. The amount of water inside is very large. One more thing here, we see there is a shift of the characteristic signal in hydrogel shift compared to the signal in cellulose, meaning that in hydrogel the structure is different. Of course, the cellulose chain is still kept, but the structure, the hydrogen bonding between the cellulose chains is changed after making hydrogel. Of course, if we want to confirm about the structure of hydrogel, we should do with the NMR, but just now the results of NMR is not come out. But I think I will show, I think in another presentation. But in this work, we just confirm that the hydrogel, the structure of cellulose chains in hydrogels is different from the cellulose itself. Okay, and here we also investigate the morphologies of materials. This is SEM emits a hydrogel, and we also, because we want to see inside of hydrogel, so we see through FIB SEM. Here in the left side, you see, please look at in the left side, you see the FIB SEM. Of course, the surface is not smooth, but inside the hydrogel, there is a lot of the void. You see here. This void is also for absorb water. When water is absorbed in hydrogel, it can be water can be filled in this void. And that's why we estimate, we expect that our hydrogel can absorb a large amount of water. Here we study the swollen ability. It is water absorbent. The water absorbent is calculate according to this equation. Yes, it's very easy way. We measure the initial weight of hydrogel, and then we input in water media or in acid or in base. So the weight of hydrogel and then we measure the weight of hydrogel at an interval times. Here you see in the figure, when we immerse the hydrogel in water, pH is equal 7. Oh, you see, so it absorbs water after about 60 hours. After 60 hours, so the weight of hydrogel may be stable. It means the maximum amount of water is absorbed. But you can see when we immerse the hydrogel in acid or in base, it's quite different. Our materials seems to be absorb the base more than acid or water. Here with acid we use acid with pH around 4, and in the base pH around 9. So we can conclude that our hydrogel is quite stable in water and in acid, but it's not stable in base. I mean, it's very easy to be degrade in base. Okay, and then this is thermal properties. We want to know how it can resist to the thermal. Okay. Sorry. Sorry for what? Okay. This is TGA. We investigate the thermal resistance of the hydrogels. Here you see in the TGA of our materials, it gradually the weight of the material is gradually reduced. It means water inside hydrogel is gradually removed. It's not removed. It's not subtly removed. So it means our hydrogel is very gradual to be removed water. It is also one more thing. Until around more than 100 degrees C. So it's the mass change is around 2%. Just exactly is 1.9%. It's very small amounts of water. I'm sorry, it's very small amounts of waste. It means our hydrogel is very high thermal resistant. More than 100 degrees C. It's up to more than 100 degrees C, the mass is reduced. Another kind of thermal properties is here is DSC. In this DSC, we can see in this DSC, we can see the this to peak from minus 50 to around 90 degrees C. There is no change in structure of the hydrogel. So it's very suitable to use for such application. For example, for applications such as in medicine, because in medicine you don't need to use materials more than 100 degrees C. From 89.8 degrees C, there is a peak. This peak is attributed. This peak. Okay. Okay, this peak is attributed to the change in structure of hydrogels. And then there is a very large peak in at 137.5 degrees C. This peak is associated to the completely remove of water. It means all water is removed at this this degree C. So maybe we can conclude that in such a case, the hydrogel is quite stable up with the thermal. It means more than 100. It can be used in the range of very last temperatures. Okay. Okay, so now we already investigate about the thermal properties. One more properties we concern is the mechanical properties. How is hard? How is tensile? Here is some mechanical properties of the hydrogel, and hydrogel in either water or in acid or base after 60 hours. In the first row, you can see the young modulus, tensile and elongation at break of hydrogel. So after we immerse in water, acid or base for 60 hours, we also take out the sample and we measure again. Here you see the young modulus of hydrogel is increased after immersed in water, acid or base. It means after immersed in water, it becomes harder. It's quite strange. This property is quite strange because after immersed in water, it's become harder. But the other thing is tensile strength. Tensile strength is after immersed in water, the tensile strength is reduced and elongation at break is reduced. But after immersed in acid and base, the tensile strength increase. Of course, a little bit increase. It may be explained that the proton in the media, it have acid or base. It can make the cross-linking agent become harder. So that's why the hydrogel is become harder in acid and base. It's quite strange. It's quite interesting properties, but we think we will investigate more about these properties. Okay, and because so we already synthesis and characterize some important properties of hydrogel, but please keep in mind that, please keep in mind that hydrogel itself is not, oh, I'm sorry. What is the problem now? I'm sorry. Okay. Okay. Just now I mentioned how to prepare the hydrogels based on cellulose, and I also show you some properties we characterize. But please keep in mind that hydrogel itself has not wide application. But when the hydrogel just now we prepare itself don't have wide application. But when we add some agent inside the hydrogel, then this material will have some new properties. So the key research, the main point here is how to add some agent inside the hydrogel to prepare the materials for the purpose of application. So now I want to change into the application. The first application is electrical conductivity materials. Electrical conductive materials can be used in battery. Of course, here I want to show you the battery. I want to mention something about the battery first. Nowadays, battery is very common, very popular in our life. This is a battery structure. It contains an anode, and cathode, and electrolyte membranes. Between this anode and cathode region, there is a separator. Nowadays, we concern about the flexible battery. For example, when we want to wear a watch in our hand, so we need, of course, we need a battery also very flexible. So if we want to prepare a battery flexible, we also need anode, cathode, electrolyte membranes, and separator also flexible. It means it's easily to remove. It can be bent or it can be shredded, but it still keeps the structure of a battery. The battery here can be a lithium battery or a fuel battery. Now, because of the development of our life, so we concern about lithium battery or fuel battery. Fuel battery is usually made from hydrogen or some kinds of fuel. So, how to make a battery which is flexible? So we have to find materials to make an anode or cathode or electrolyte membranes which is flexible. So one very personal candidate is also hydrogel. Here in this path of battery, anode, cathode, and electrolyte membranes must be made from electrical conductivity materials. So that's why in our group, we think that we can use either anode from hydrogel or electrolyte membrane from hydrogel. Why? Because we can add some agent inside the hydrogel to make it become electrical conductivities. And then from this, because it's a hydrogel, so it's very flexible. And we can make it either anode or electrolyte membrane. So in order to do this, we propose the procedure to prepare this kind of materials. First, I want to show you how can we prepare these kinds of materials. In this procedure you are seeing now, please look at the screen. Here we prepare the flexible anode. Also from cellulose, we also add the sodium hydroxide solution and chlorhydric acid solution to make the cellulose colloids, and then we prepare hydrogel. This already prepared, already done in our laboratory. And then finally we add graphene colloid As I mentioned before, because hydrogel has a 3D network, it can trap some small molecule. So we take graphene colloid as a small molecule and trap it inside the 3D network of hydrogel. Because as you may know, graphene is a very good electrical conductor. That's why we add graphene inside the hydrogel. Then we can make hydrogel with this hydrogel with graphene can be used as a flexible anode. It's a material to prepare a flexible anode for battery. So in this work, we already successfully insert graphene inside the 3D network of hydrogel. One more thing. Now we want to prepare electrolyte membranes. This one is also a component of a battery. Also from cellulose, we prepare cellulose colloid, and then we make the hydrogel. The only thing different is we also add the salt of lithium inside. This one you see in the step 6. This solution is for we want to add lithium ion inside the hydrogel, to get the membranes, which is used for lithium battery. So this way is so based on hydrogels, we can prepare hydrogels with electrical conductivities. Okay, so here is some properties of materials we prepare. With the thermal properties, we also concern. This is TGA thermogram of the materials. This is you see the thermogram of hydrogel, thermogram of graphene, and thermogram of hydrogel with lithium salt. Of course, after we add some lithium, the thermal resistance also a little bit reduced. But when we add graphene, the thermal resistance is increased compared to hydrogel. So it meaning that we can use these materials for prepare the battery. It's suitable to prepare the battery. And okay, so meaning that graphene can help to improve the thermal resistance of the hydrogel. We also investigate the DSC thermogram of sample. Here is the hydrogel graphene, then hydrogels with lithium salt. You can see the thermal properties of hydrogel and hydrogel graphene is quite similar. This conclusion is in good agreement with the properties from TCA just now I showed you. And for this, of course, we concern about electrical conductivity. Here, please keep in mind that the electrical conductivities of hydrogel with lithium is ion conductivity. So the measurement is quite different. And the hydrogel and the sample of hydrogel graphene is electrical conductivity is quite different between this kind of conductivity. The first one is ion conductivity. The second one usually is electron conductivities. So we also measure the resistivity of these materials. With hydrogel, the resistivity is around 3.5. or multiply meter. But when the lithium ion salt is added, so the resistivity completely reduced. Is greatly reduced. And then when graphene is added, the resistivity is reduced more. It means the conductivity increased very much. So hydrogen graphene is the highest in electrical conductivities. So it is very suitable to use as an anode. Also, the hydrogel with the lithium salt, the lithium ion, is also have very high electrical conductivities. It's also suitable to be as a electrolyte in a battery, in a lithium battery. These results, we just use very small amount of lithium salt and graphene. The lithium salt is only about 5% weight by weight, and graphene is also 5 to 7% weight by weight. So now you see, only add very small amount of the agent, so we can get the sample with high electrical conductivity. Okay, so this is our some work about the application in electrical conductivity materials. Here in the next part of application, I would like to show you another application of hydrogel. So it is, I want to report about the application is antibacterial membranes. We also can make hydrogels become antibacterial membranes. So here is how we do. Actually, hydrogel itself is not antibacterial membrane. But when we add some ingredient or some agent, it can make a antibacterial membrane. In such a case, we select silver to add. Why we add silver? Of course, you may know silver is a very good antibacterial agent. So when we can insert silver inside hydrogel structure, then we get an antibacterial membrane. The problem is, how can we keep the silver inside the hydrogel to make a stable hydrogel? So that is our work. In our work, we do like that. With hydrogel, first we also immerse in silver salt, for example, silver nitrate, and then the silver ion can go through the hydrogel structure. Yes, as I mentioned before, inside hydrogel there is 3D network, and it can keep some ion. Then here you see iron is inside the hydrogel, and then we make chemical modification. That is a reaction, the reduction reaction, and then silver ion make a nanoparticle of silver. With these nanoparticles, it is easy the antibacterial agent. Why we have to immerse silver nanoparticle inside hydrogel? Because we want to make a stable materials. If we only silver nanoparticles. It will be easy to be silver nanoparticle is very easy to be stick together again. And when the particle is bigger, so the antibacterial activities will be reduced. By the way, to disperse nanoparticle inside a hydrogel, so it is very easy to keep it separate. Okay, so now how we do in our laboratory? This is a procedure to prepare the antibacterial membrane. Also from cellulose, we make cellulose colloid. Yes, it's very popular as you see this now. And then we add, we make the hydrogel by adding acrylic acid, ammonium persulfate, and methylene acrylamide. And then we add silver nitrate. After add silver nitrate, so we get the hydrogel with the silver ion inside. Finally, we make the reduction reaction. We use sodium boron to make the reduction. Then after this step, after the step of the seventh step, so we get the nanoparticle of silver. So this one is hydrogel silver. Hydrogel with silver is antibacterial membrane. Here we also concerned about the properties of this membrane. I would like to show you some properties of the materials we already prepared. Okay, after this, first I want to show you the results from antibacterial activities. With this kind of membranes, we change the amount of silver in hydrogel, and we test with several kinds of bacteria. Here we use we test with 4 kinds of bacteria, and we see that, of course, when the amount of silver is 0, it cannot. The materials, it means hydrogel have no antibacterial activity. And then when we increase the amount of silver in hydrogel, you see here from 100 to 200 and until to 2000 milligram of silver in per gram of hydrogel. So you see, with E. coli, this one is very to be killed by these materials. But the last one is Ecloacia is the last one here. You see, is quite difficult to be killed. But anyway, until 2000 milligram microgram per gram of silver. So the materials have the antibacterial activities. In the future, of course, we also want to test with another kinds of materials. We don't actually this test we don't do in our laboratory, but we send our sample to another laboratory to test this. But hopefully in the future we can get more data, more results with the antibacterial activity of our sample with the other bacteria. One more thing we also concern is after being use of antibacterial membrane, how it can be degraded is also our concern, because just right now we also concerned about the rabies. Rabies is many is manywhere in many places. We see rabies, and there is no useful solution to solve this problem. So with this membrane, when we prepare, how can it be degraded? So now we also investigate the degradation under artificial weather test. Of course, in the artificial weather test, is we want to speed up the degradation of the materials, but meaning that in the same way, is meaning that it's also be degrade under the weather under the weather. Our test is UV radiation for 8 hours, and then vapor and thermal for 8 hours. This is repeat for 3 cycles. This is hydrogel with silver before UV radiation, and then is this after this before in the left side is after before the weather test, and the right side you see is the after the weather test. You see on the surface of sample, first the surface is quite smooth, but after the weather resistant test, you see here there is a lot of point on the surface, meaning that it's easily to be degraded. So in order to be quantify, we look at the weight retention. Here you see hydrogel. Hydrogel after 3 cycles of weather resistant test, so the weight reduced. So it only now after 3 cycles, only 55% remain. But for the hydrogel with silver, the weight is less, only 30% remain. One more thing for the tensile. The tensile of hydrogel with the silver is first, when we you see here, please look at the figure in the right side. Okay, please look at here. This is the tensile strength of hydrogel before weather resistant test. The tensile strength is about 3.12 megapascal. But after silver is added, so the tensile is a little bit increased. But interestingly, after the weather resistant test, you see here, after 3 cycles of weather resistant test, the tensile of hydrogel is still 1.20 megapascal. But here, please look at this. The tensile properties of hydrogel with silver is 0. It means hydrogel with silver is very easy to be degraded. This may be explained that because of the presence of nanoparticle silver inside the hydrogel, so it is easy to it can be speed up the degradation under UV radiation and vapor and thermal weather resistant test. So that's why when we add silver and according to our process, so the hydrogel become antibacterial membranes. And also these antibacterial membranes have the property is easily to be degraded under the weather resistant test. It means when in the nature, it's very easy to be degraded under the light, the water, and also some condition of environment. Okay. Okay. Now come to the conclusion. In this work, we already proposed the procedure for the preparation of hydrogel based on cellulose. And the second one is cellulose hydrogel has great potential to apply in various fields, either in bacterial, either in bacteria or in antibacterial membranes. Okay, and finally, this research is funded by Ministry of Education and Training under the project. I would like to thank to my colleagues and students in School of Chemical Engineering, Hanoi University of Science and Technology. And last but not least, thank you for your attention.
Okay, thank you very much, Dr. Nguyen Thu Ha, for the impressive and insightful presentation and very clear for the presentation. Okay, now let's move to discussion session. If everyone have a question to Dr. Nguyen Thu Ha, you all can raise your hand or write on the chat box. Come on. All right. Very clear presentation, maybe.
Yes, maybe I know that you are in the pharmacy, the pharmacy field. Maybe it's not so familiar with this work, but actually in our laboratory now we try to prepare the materials for the bio application and also pharmacy. That's why I really want to listen about any questions or comment. Anything is also very helpful for us to enhance our research work.
Yeah, based on the presentation, the hydrogel film can be used as a drug delivery system, right? We can conjugate it with the maybe drug, and then this hydrogel film can be used as a system to deliver the drugs.
Oh yes, I think so. Actually, it's also one of our research. After we prepare the hydrogel, we can use it as a drug delivery, because you see the structure of hydrogel is very flexible and also water inside. So as long as we have a small molecule and the molecule is suitable to be inserted in the 3D structure, so we can prepare any materials we like. So that's why I also think about the drug delivery. But just now we just in very initial in very first step. Hopefully one day I can present about the hydrogel with the drug delivery, because we are already interested in that field of work.
Okay, Dr. Nguyen, there are two big procedures, right? Using the physical procedure or chemical procedure. What you did in your lab is using the chemical, right? Why you use the chemical procedure?
Yes, yeah. Actually, there are two kinds of the cross-linking in hydrogel. You can see here. The first one is physical linkage. Okay, I will show you here. Okay, please wait. Okay, there are many kinds to make the physical linkages in hydrogel in this hydrogel structure, but actually all of them is very weak. The only one this one is quite strong, but because it's strong, so it's very hard, so very difficult to insert any small molecule or any ion inside the 3D structure. That's why when we make the chemical cross-link, here is an example. Yes, of course, it's it's reported in some literature that we can use some kind of cross-linking agent to make the 3D network. But in our research, we prepare the hydrogels, and we also use here you see methylene acrylamide to make the hydrogel. This is one of chemical linkages, cross-linking junction, and for this, it's very flexible. Of course, it's been the chemical linkages is very strong, but still flexible. That's why we select this to prepare the hydrogel.
Okay, but the cross-linker is not only MBA or methylene bisacrylamide, right?
Yes.
There are a lot of cross-linker.
Here I use two. The first one is acrylic acid. Okay. Now, this one is similar to a monomer. And this monomer will attack the cellulose. And then we use ammonia pair sulfate to make the connection between the two acrylic acids in two cellulose chains. And then finally we use N-methylene bisacrylamide to make it become cross-link.
Okay. Thank you. And the application of the hydrogel film, one of the application is use it as a battery.
Yes.
Yes. Have you compared the lifetime of the hydrogel film battery and the conventional battery?
You mean can you repeat the question?
Have you compared the lifetime?
Actually not yet. We don't until now we have not compared yet. But I think the question is also very good comment for us. We will do later.
Yeah, so if the lifetime is longer, it will be more good. It's better to use the hydrogel film.
Yes. Hopefully. But until now we can get some very good results, but I don't have time to insert in this presentation yet, because now we already find the relationship between silver particle and the antibacterial activities. So we find the optimum particle silver, the optimum, the optimum size of particle for the antibacterial activities of these materials.
Okay. So, is there any question from the participant?
But hopefully one day I have chance to present more research about this, because you please understand this also not we just investigate about this topic. So this very in early step of our research work. But maybe one day I can show you more results on this.
Yes. Yeah, we wait for the more result of your research.
Yes, hopefully, and hopefully one day we have the very good. I think we can make some collaboration on this research work.
Yes, of
because
course.
because you are I think you all of you are experts in this field about the antibacterial activities. Please help me to you may help me to mention to suggest. So apart of silver, anything can be used for antibacterial activity. Maybe you can suggest me. So.
And then compare it with the standard drug, maybe.
Yes. Maybe I can use, or if I don't put the if I don't insert silver inside, maybe I can use some drugs inside this hydrogel. Maybe.
Yes, but maybe if you insert drugs, you need the conjugate agent.
Yes. Yeah. To make it stable.
Able to link,
Yes.
able to react.
Yes, maybe. I think so.
Long journey to go.
Yes, that's what I think in this field there are many things for us to investigate.
Yeah. Okay, because I think there is no question from the participant. I would like to say many thanks to Dr. Nguyen Tuha for the excellent and insightful presentation. Give applause to Dr. Nguyen Tuha. Okay, I will return it to MC. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you and see you next time.
Yeah.
Right. Thank you very much, Mrs. February. And also, once again, thank you very much, Prof. Nguyen. And I would like to inform all participants that our committee have shared the attendance list as well as the evaluation questionnaire in the chat box. So please kindly spare a minute to fill on attendance list and the evaluation questionnaire. And now for the appreciation, our committee would like to give Prof. Nguyen and Dr. February a certificate. The certificate will be given by Mrs. Apothekar Medi Utami Putri, Master of Science PhD virtually.
Professor Nguyen, thank you so much for giving the very nice lecture to our students. Also, everyone here. I really hope that everyone can get the value and the benefits from your lecture. And I also really hope that it can be the start of our continuous collaboration. Once again, thank you so much. So this is the certificate as the symbolize our gratefulness. Thank you.
Thank you.
Thank you so much. And also would like to give the appreciation to Apotheker Febrina Malaysia Putri Magister Pharmacy. Thank you for being the nice moderator to moderate today's lecture. Thank you so much.
Thank you so much.
Okay, so I will return it to MC. Thank you.
Thank you, Mrs. Mady. And ladies and gentlemen, now we are going to take a picture for our documentation. We would, if you please would turn on your video and please one of the committee to guide this photo session. Thank you very much.
Okay, I will take the screenshot. There are 3 slides. For slides one, two, three. For the second slide, 1, 2, 3. And the last slide, 1, 2, 3. Thank you, everyone.
Thank you very much, everyone. Now, ladies and gentlemen, again, we would like to remind you all to fill in the attendance list that we have shared in the chat box. And for your reminder, the next lecture will be held tomorrow on Wednesday, 24th August 2022 with two lectures. Lecture number 5 from the Associate Professor Dr. Seiya Mizuno from the Lab Animal Resource Center, University of Tsukuba, Japan, that will start at 10 a.m. GMT +7, and lecture number 6 by Dr. Swari Jasiel, Assistant Professor of Data-Driven Chemistry at NICE, Japan, that will start at 1 p.m. Jakarta time. The Zoom will be open 30 minutes prior to the lecture starting. And finally, we have come to the end of this event. May all of us get the value and benefits from today's lecture. Thank you very much for your kind attention and participation in this summer course. I am Fanny Annabelle signing off and see you tomorrow. Wassalamualaikum warahmatullahi wabarakatuh.